In this video I'm going to be talking about the SOR method. So SOR method. Now SOR stands for successive over relaxation. Spell over. Successive over relaxation. So this is another indirect method for solving linear systems. Now what successive over relaxation does is it has a look at the behaviour of an iterative method. So here I've got a set of axes. K, this is going to be the number of iterations, and this is going to be the value of a solution xk, and this dashed line, I'm going to say this is the actual solution. So remember, we're only ever estimating. Okay, so we could have a convergence behaviour like this. Okay, so this is nicely ordered. Okay, it's what we call monotonic conversion behaviour. So if I was to draw a line through these points, what you're seeing is as the solution, or as we go through our iterations, our solution is getting closer and closer to our actual solution, which that's what we want. Oh, you know, we could also have another form of convergence and doing the same set of axes here. So this is, again, is going to be the same xk. Okay, that dashed line is, I'll do better than that. That dashed line is, let's say that's our actual solution, x star, which we don't know what it is. But we've also got, if we had this sort of behaviour, so what's happening here is our estimate is oscillating around the exact solution. Now, it's going to converge, and it might converge faster than the monotonic way, but it's still oscillating. Now what successive over relaxation does, it seeks to speed up both of these types of convergence. And what I mean by that is, I'll just use another colour, with monotonic conversions, okay, so this is our first estimate here, okay, this is our second estimate. Now the difference between the first estimate and the second estimate, let's say if I was to increase that, I'd get a value there. And same here, let's say I was increase this distance here, I get a value here, etc. So what we'd have is we'd have what we call an over relaxation. Okay, so we're improving the convergence of our method. So that's when we have monotonic convergence. Okay, what happens when we have oscillatory convergence? So where our solution is oscillating, so our next estimate is too high, our next estimate is too low, etc. Well, here we need to slow down. Okay, so we need to, let's say we reduce that distance from the first estimate to the second to say there, and let's say we reduce this distance to say there, okay, and this distance, etc. So if I was to draw the line for our new values, you can see we'll have a quicker we'd have quicker convergence. So in this case we need to what we call over relax. So this is over relaxation. So this is all dependent upon our system. So this is where we need to apply over relaxation. If we have oscillatory convergence, we need to apply what we call under relaxation. Okay, so this is what the SOR method seeks to do. It speeds up our solution. Usually it's a Gauss-Seidel method, so it seeks to speed up the Gauss-Seidel method by giving it either a little bump, giving it a little sort of push in the right direction, or if we need to under relax, we slow it down somewhat. Okay, so let's see what that means. Okay, so the SOR method, I can write out here. So for the ith value, or ith unknown, this is going to be equal to 1 minus omega, and I'll explain what omega is in a minute, and that's multiplied by our current estimate of x, and this is plus omega over our main diagonal element a, and this is bi minus a sum of j equals 1 to I minus 1, and this is multiplied by the lower triangular element aij times xj k plus 1, and we've got another summation, and this is j equals I plus 1 to n, where n is a number of system equations in our system. That's multiplied by the upper triangular element aij, multiplied by xj, and that's our current value. Okay, so this is the SOR method. Okay, eagle eyes amongst you may notice, but this is our Gauss-Seidel method. Okay, it's Gauss-Seidel method. So essentially what we have is we have 1 minus the current solution, okay, plus omega, so this thing that looks like a W is a Greek letter omega, times, and I'm going to say x bar, where x bar is our Gauss-Seidel solution. So omega, if omega is greater than 1, what we'd say in here is if omega is greater than 1, we're using less of our current solution and more of our updated solution. Okay, so this is where we over relax. So when omega is greater than 1, we have over relaxation. This is where we want to give a bit of a speed up, a bit of a speed bump, so where we have monotonic conversion. When omega is less than 1, we have under relaxation. Okay, so this is where we want to slow it down. So if we have an oscillatory convergence, so we keep overshooting the solution, we want to slow it down a bit, and this is where we have omega. So if omega is less than 1, this number here would be greater than 1, and this number here would be less than 1, so we're using more of the current solution and less of the new solution, so that's slowing it down. Now in reality, omega is in the range 0 to 2. Okay, so we never want to overdo it. We never want to sort of more than double. Okay, so that's and omega is known as the relaxation parameter. Okay. Now the actual value of the relaxation parameter will depend upon the system that you're solving. Sometimes it'll be less than 1, sometimes it'll be greater than 1. It is possible to calculate the optimum value of our relaxation parameter, and there's a section in the notes, if I just recall what section that is. If you have a look at example 7.7 from the notes, that will show you how we calculate this, or we can, for certain systems, calculate the optimum value of this relaxation parameter. Sometimes we can't, and we just calculate this via some sort of numerical experimentation. Okay, so what I'm going to do now is actually have a look at a worked example. This is the same worked example which we've been using previously. If you've watched the Gauss-Seidel and Jacobi videos, so this is the same 3x3 matrix. Okay, so it's 3x3, we have 3 unknowns, and we have a right hand side vector 4, 3, 9. Okay, in these calculations, I'm going to say, like I have with the previous Jacobi and Gauss-Seidel, I'm going to start with 0 guess values, and I'm going to use a relaxation parameter of 1.2. Okay, so our SOR method for this, so for the first unknown in our system, x1, our SOR method is going to be 1 minus omega, so 1 minus 0.2 is 1 minus 1.2 is 0.2, and that's multiplied by our current guess value. This is plus omega divided by 2, which is the main diagonal element, and then essentially we've got the Gauss-Seidel method. So that's b1, which is 4, minus x2, and we haven't yet calculated that, so I'm using the current value or the case value, and similar for x3. Okay, for the second unknown, again 1 minus omega is minus 0.2 times, that should have been a 1, not an I, times our current value of x2 plus omega over 3, and that's multiplied by 3 plus x1, but we're using the value we just calculated, and that's minus 2x3 using our current value. And finally, for x3, our new solution, or our new estimate, is still 0.2x3 times the current one plus omega, which is still 0.2 over 4, and that's 9 minus our new value of x1 plus 2 times our new value of x2. Okay, so that's our SOR method. Let's have a look at the iterations. So for the first iteration, I'm going to have minus 0.2 times 0 because we're starting with 0 starting values, plus 1.2 over 2. We're going to have 4 minus 0 minus 0, and that comes out at 2.4. For our second unknown, again I've got minus 0.2 times 0 plus 1.2 over 3, 3 plus that 2.4 I've just calculated, minus 2 lots of 0, which is the current value of x3. And finally, the third unknown, again minus 0.2 times x3, which is currently 0, plus 1.2 over 4, 9 minus our new value of x1, which is 2.4, plus 2 lots of our new value of x2, which gives us 0.576. Okay, so that's the first iteration done. Second iteration, so this time minus 0.2 times 2.4. And this is plus 1.2 over 2, 4 minus 2.16 minus 0.576. That gives me 0.2784. x2 for the second iteration, 0.2 times 2.16, because that's the one we calculated from the previous iteration, plus 1.2 over 3, that's 3 plus 0.2784, which we just calculated, minus 2 lots of 0.576. Okay, and that equals 0.4186. And x3 is minus 0.2 times 0.576 plus 1.2 over 4, 9 minus x1, which is 0.2784, plus 2 lots of x2, which is 0. Go away, sorry, that was Daria coming through. Hang on, where am I? 0.4186. And that equals 0.0524. Okay, I've run out of room there. I'm going to rewrite that here. 0.0524. Okay, so you can see it's more complicated. There's a couple more calculations involved, and I hope you're starting to realise now doing these by hand is quite tedious. So that's why we tend to use computers. But that's the successive over relaxation method.